In the last lecture, we have seen how to find out the terminal voltage of a 3-phase transformer when it is loaded. It is similar to what we have done in a single phase transformer. In fact, in a single phase transformer, we have defined the quantity percentage regulation of a transformer as the terminal voltage at loaded condition, V at loaded, V at no load minus V at load divided by V at no load into 100. A similar definition of percentage regulation applies for 3-phase transformer. However, in this case percentage regulation is defined as line voltage at no load minus line voltage at load divided by line voltage at no load into 100. However, the formula will be the same as we have seen in our last lecture. The loaded terminal voltage was given by Vp equal to this. Following that, Vp, the loaded phase voltage Vp equal to no load phase voltage Vp dash, which is the applied voltage, minus Ip Req cos phi plus Xeq dash sin phi. Hence, Vp dash minus Vp by Vp dash equal to Ip into Req cos phi plus Xeq dash sin phi by Vp dash, which can be written as Ip by Ip rated into Ip rated Req dash by Vp dash cos phi plus Ip rated Xeq dash Vp dash sin phi, which will be equal to x into epsilon r cos phi plus epsilon x sin phi, where epsilon r is the per unit series resistance of the 3-phase transformer, epsilon x is the per unit series reactance of the 3-phase transformer, and x is the percentage loading. So, the formula is identical to that of a single phase transformer. The other important operation parameter of a 3-phase transformer, as in the case of a single phase transformer, is its efficiency, and efficiency of a 3-phase transformer can also be found from the no load test data. For example, if we go back to our previous example of that 11 kV by 400 volt 150 kVA single phase transformer, 3-phase transformer, with this data, no load and short circuit test data, we can find out its efficiency under any loading condition. So, the no load test had a total power loss of 2 kilowatt. So, the core loss P core of this transformer equal to 2.0 kilowatt. From the short circuit test data, we find that the 3-phase power loss at rated line current at 8 ampere line current is 3.5 kilowatt. Therefore, the for at any the core loss, copper loss at any operating condition is equal to 3.5 kilowatt into the load current IP divided by 8 divided by root 3 whole square. For the particular operating condition that we have said, that is 150 kVA, which is the full load current, full load, and 0.85 pf lagging load. We have found that in that case the IP on the low voltage side was 216.5 ampere and Req dash for this transformer was 0.0241. Therefore, P copper loss under the stated condition was 3 into I P square into Req dash, and this comes out to be 3.39 kilowatt. So, the core loss of the transformer is 2 kilowatt, the copper loss is 3.39 kilowatt, and power output of the transformer P0 equal to 3 Vp Ip cos phi. This comes to 121.77 kilowatt. Therefore, the efficiency of the transformer under this operating condition of 150 kVA 0.85 pf lagging, nu equal to P0 into 100 divided by P0 plus Pc plus PCU. This comes to 95.76%. So, we can find also the efficiency of a 3-phase transformer in a manner similar to what we have done for single phase transformers. While these are important performance parameter of a transformer, it is also extremely important to know what will be the temperature rise of a transformer when it supplies some load. Now, this cannot be found experimentally from either no load test or short circuit test, since during no load there is no current flowing in one of the windings, the transformer current is very less, hence the copper loss is almost absent, and during short circuit test only a very small fraction of the line voltage is applied, therefore, the core loss is almost 0. In order to find the temperature rise of the transformer under certain loading condition, it is necessary to emulate both the core loss and the copper loss simultaneously. And we have seen for single phase transformer, this can be done by the so called back to back or Schumpner test. Similar test for the heat run test can also be conducted for a 3-phase transformer. So, in a single phase transformer, what did we do? For back to back test, we supplied the primaries of the transformer from the same supply, connected them in parallel and connected the secondaries in series, so that the induced voltage in the secondaries oppose each other. This we connected to the rated supply, and this ammeter, wattmeter we connected to a auxiliary source. A similar arrangement has to be done for a 3-phase transformer now. So, let us say we have a 3-phase transformer. If any particular site is star connected, what we should do? We have to connect them, those star windings, in series, while the other side has to be connected in parallel. So, the following figure shows an arrangement. Let us say this is the 3-phase mains supply line, and you have connected the one of the winding in parallel. This is one winding of one transformer, HV or LV. This is the other winding of the same transformer. So, the other winding, the secondary winding are also star connected. So, these windings are to be connected in series the polarities should be such that the induced voltages oppose each other. So, if this is A1 terminal of transformer 1 and this is A2 terminal of transformer 1, then this should be A2 terminal of transformer 2 and this should be A1 terminal of transformer 2. So, if you connect them in series, the voltages will oppose each other. However, how do we apply the auxiliary voltage here? For that, here we will need a separate transformer. Separate auxiliary 3-phase transformer will be necessary. So, in order to supply that, we will supply it from a auxiliary transformer like this. This is how it will not be variac anymore, it has to be supplied from a separate 3-winding auxiliary transformer. Now, if one of the windings are delta connected, then the arrangement becomes somewhat simpler. Let us say this is the delta connected winding. You open the delta at both the windings at one point. And connect these two open ends in series, and then you can connect a single phase auxiliary transformer like this to circulate the necessary current through the. So, this is for back to back test with star star connected transformer. This is back to back test with star delta transformer. Now, how do you determine which connection to use in a particular application? Normally, star and delta connection are the most common type of connection. You can see that if you have a star connected side with its neutral set of winding with its neutral earthed, then the maximum voltage that the term windings will have with respect to ground will be V line by root 3. On the other hand, if you have a delta connected winding, then in the case of a line to ground fault, the potential of the other line terminal can go to as high as VL. Therefore, for the same voltage rating of the winding, a star connected winding will require lower insulation and hence will be somewhat cheaper. That is why for very high voltage transformer, generally star connected high voltage side is usually star connected. Now, if you have to supply loads which are unbalanced, then it is better to have a star connected side with the neutral made available, so that the line current can, the unbalanced current can flow through the neutral. If there is, the currents are IA, IB and IB and IC, and when the neutral current is IN, then IA plus IB plus IC equal to minus In. Now, if the primary of this is delta connected, then the reflected winding currents IA dash, IB dash, IC dash will also be unbalanced. They will not add up to 0. On the other hand, on the line only positive and negative sequence component can flow, that is the line currents IAL, ICL, IBL must add up to 0 this is always 0. However, the induced winding currents are do not add up to 0. So, there is the 0 sequence current I0 equal to In dashed by 3 that circulates through the closed delta. This is necessary to prevent distortion of the secondary side voltage. So, if you have a star connected winding supplying unbalanced load through a neutral connection, then the other winding should preferably be delta connected. So, another reason that decides whether a winding should be star connected or delta connected is the consideration of harmonics. While discussing the magnetization phenomenon of a single phase transformer, we have seen that in a tactical transformer the core is operated near the saturation point. Therefore, if the applied voltage is sine wave, the flux is also be a sine wave. However, the current will no longer be a sine wave and it will have the magnetization current will have a predominant third harmonic component. Now, the third harmonic the phase angle between IAM1 and let us say IBM1, this is 120 degree, but for the third harmonic this is 360 degree. Therefore, the third harmonic magnetization currents are cophasor, therefore, they do not add up to 0. It is something like that 0 sequence component. Since they do not add up to 0, it is necessary that one of the windings provide a path for this third harmonic component to flow, so that the flux and the induced voltages are almost sinusoidal. So, the preferred winding connections will be delta delta, delta star or star delta, of which we have seen that if one side is very high voltage, then that side should preferably be star connected, the other side may be delta connected. So, from the transmission level, the high voltage side winding will usually be the star connected winding, while the other side will be delta connected. The delta-delta winding is used specifically for low voltage transformer that needs to supply a very large current, because in a delta-delta winding the winding current is less than the line current, therefore, the cross section of the windings becomes smaller. For the same reason, the star-star connected transformer is not very much in use, particularly the isolated neutral star-star connected transformer. Let us see the problem that may occur due to a isolated neutral star-star transformer, where the path for this third harmonic current do not exist. So, this is a so, suppose we have applied a balanced 3-phase voltage to this isolated neutral winding. The other winding also is star connected and does not provide a return path for the third harmonic current. In which case, since there will be no third harmonic current, the no load current will be almost sinusoidal and the flux will be non-sinusoidal, and the induced voltage E A n will also be non-sinusoidal with a predominant third harmonic component. So, the E A n can be written as E A sin omega t plus E A 3 sin 3 omega t. Now, neglecting the impedance of the transformer, impedance drop of the transformer at no load, this should be equal to the applied voltage. So, for all the 3 phases we can draw the following block diagram. Let us say these are the applied phase voltages with respect to the applied phase voltage with respect to the supply neutral. Now, what will happen in this case? Here the voltages induced will have a fundamental component and a third harmonic component. The relative speed of this third harmonic voltage is with respect to A n is 2 omega. Therefore, the phasor diagram in any case will look somewhat like this. And this point, the end point, will keep moving at a speed 2 omega. Because the frequency of this is 3 omega and this is omega, this does not rotate, this one rotates as a speed of omega t. So, this point will be rotating at a speed of 2 omega t. This is called the oscillating neutral phenomenon and it is highly undesirable. That is why a isolated neutral star-star connection is not used. Let us see what might happen if a isolated neutral connection is used through an example. So, let us consider that we have a 3-phase transformer. It supplies mixed impedance type load. The phase A load is 230 volt, 15 kilowatt at 0.8 lagging power factor. This is 230 volt 25 kilowatt with 0.9 lagging PF, and phase C a 3-phase transformer is supposed to supply this kind of loads: 230 volt, 35 kilowatt at unity power factor. Now, find out, let us say when the transformer is delta delta connected with no neutral available, and the high voltage side is 11 kV and the low voltage line, this is 11 kV, line voltage is 11 kV, HV line voltage, and LV line voltage is 400 volts. Let's try to find out the voltage across each load phase. Now, from the given load data, these loads are star connected though, but the neutral of the load is isolated. Since the transformer is delta connected, the neutral is floating. So, the phase A load, the load connection is somewhat like this. This is phase A load Z A, this is Z B, this is Z C, this is the isolated neutral N, this is voltage V A, this is the line current I A. Similarly, this is the phase voltage V C, this is the line current I C, this is the phase voltage V B, this is the line current I B. Now, from the given data, what is Z A? Z A equal to V phase square divided by P A cos phi A angle of cos inverse phi A, and this comes to 4.41 ohm angle 36.87 degrees. Similarly, ZB equal to 2.35 ohm angle of 25.84 degrees. Phase ZC equal to 1.51 ohm angle of 0 degrees. Now, this is a delta delta connected transformer. The input side is connected to a balanced 11 kV source, and hence the low voltage side also you have balanced 400 volts supply. Let us assume ideal transformer. Therefore, it will be convenient to replace the star connected load by an equivalent delta connected load. The equivalent delta connected load will be connected like this. This is again VA, this is the line current IA, this is VC, line current IC, and this is VB, line current IB. This is, let us call it the impedance ZAB between A and B. This is ZBC between B and C, and this is ZCA between C and A. Now, from the star delta equivalence formula, we can write ZBC equal to ZA ZB plus ZB ZC plus ZC ZA by ZA. This comes to be equal to, from the given data, 4.34 ohm, angle 13.553 degree. In a similar manner, we can find out ZCA to be equal to 8.145 ohm, angle 24.583 degrees, and ZAB comes out to be 12.67 ohm, angle 50.423 degrees. Now that we have the impedances, it is easy to find out the currents. Let us say IBC equal to VBC by ZBC. This comes to equal to 92.166 ampere at an angle of minus 13.553 degrees. Similarly, ICA will be VCA by ZCA equal to 49.11 ampere, angle of minus 144.58 degrees, and IAB equal to VAB by ZAB equal to 31.557 ampere, angle 69.577 degrees. Now that we know the currents flowing through the equivalent delta connected loads, we can proceed to find out the line current IA, IB and IC. IA is given by IAB minus ICA. This comes to be 77.28 amperes, angle 0.67 degrees. IB equal to IBC minus IAB equal to 93.78 ampere, angle minus 33.07 degrees, and IC, line current IC, equal to ICA minus IBC equal to 129.8 ampere angle minus 177 degrees. Once we know the actual line currents, it is now easy to find out the voltage across different load phases. So, VAN will be equal to ZA into IA, which comes out to be 340.8 volts angle 85.54 degrees, VBN equal to ZB IB comes out to be 220.38 volts angle minus 7.23 degrees, and VCN equal to ZC to IC equal to 196 volts angle minus 177 degrees. So, it is seen that the low voltages are highly unbalanced with the minimum phase voltage magnitude of 196 volts and the maximum phase voltage magnitude of 341 volts. So, this is the effect of unbalanced load when the load neutral is isolated. If we look at the HV side line currents in this particular case, that is IA, this is the LV side line current. LV side of the transformer is delta connected, HV side is also delta connected, therefore, IA equal to VLV by VHV into IA. This comes to 2.81 amperes. Similarly, the line current IB comes to 3.41 amperes and line current IC comes to 4.72 amperes. So, both the load phase voltage and the input line currents are unbalanced if the delta delta connected winding supplies a unbalanced star connected load. Now, let us see what will happen if the transformer was delta star connected with the load neutral connected to the delta star connected transformer. Same set of loads, but now the transformer is delta star connected. So, this is the arrangement. So, here the applied line voltage is 11 kV, balanced line voltage. These are the line currents IA, IC and IB. These are the lines A, C and B. This current winding current is IAB, this winding current is IBC and this winding current is ICA. The low voltage side is now star connected. And it supplies the same set of unbalanced load, but now the neutral of the load is connected to the neutral of the low voltage winding. And this neutral is now connected to the load neutral. So, this is ZA, this is ZB, this is ZC, this is the line current IA, this is the line current IB and this is the line current IC, and the voltage between two lines here is 400 volts. Now, since the load neutral is now connected to supply neutral, the load phases can operate independently and load phases will be perfectly balanced, that is VAN will be equal to 230.9 angle 0, let us say, then VBN will be equal to 230.9 angle minus 120 degree and VCN will be equal to 230.9 angle 120 degree. It is easy to find out the line current in this case. The line currents IA will be VAN by ZA, this comes to 52.36 ampere angle minus 36.87 degrees. IB equal to VBN by ZB equal to 98.255 amperes angle minus 145.84 degrees. IC equal to VCN by ZC equal to 152.91 amperes angle of 120 degrees. The transformer turns ratio now equal to root 3 into 11 into 10 to the power 3 divided by 400 equal to 47.63. Therefore, IBC equal to IB by N equal to 2.063 amperes angle minus 145.84 degrees. ICA equal to IC by N equal to 3.21 amperes angle of 120 degree, and IAB equal to IA bar by N equal to 1.1 ampere angle of minus 336.87 degrees. From this I can find out the high voltage side line currents. This comes to 4.244 ampere angle of minus 54.18 156 degrees, IB comes out to be 2.635 amperes, angle of minus 169.1 degrees, and IC comes out to be 3.94 amperes, angle of 88.5 degrees. So, we see that with neutral connection the load phase voltages are perfectly balanced. However, the high voltage side line currents are still unbalanced. So, that is the effect of unbalanced loading. Now, so we have seen that where a star or delta connected winding should be used, and that is why for almost all distribution transformers the second low voltage side is star connected with a neutral made available, because the distribution transformers are expected to supply single mixed 3-phase and single phase loads. Now, one other point should be kept in mind while operating 3-phase transformers in parallel. Since the parallel transformer line to neutral voltages should be same in magnitude and in phase, it is possible to connect two 3-phase transformers in parallel only when in general they belong to the same vector group, because transformers belonging to the same vector group have line to neutral voltages which are in phase. In addition, the other conditions for paralleling two transformers, namely almost equal no load voltage and the series impedance, per unit series impedance of the transformer being equal, should also be observed for paralleling 3-phase transformers.